Oh, hi there. Thanks so much for showing up for your math learning. It's Mr. Jennings, your humble math servant. And today we are reviewing the characteristics of quadratic functions. A quadratic function describes a parabola. Okay, so if I say we're to put a ball there at the point 0, 0, and here's me, and I kick it, it would go whee! It would make a parabola, okay? They're very common patterns in nature. All right. They also show up in lemonade stands or even adult business opportunities. We have these like supply and demand curves, and they create these shapes as well. It's very, very cool. They show up in lots of places. All right. We want to be able to, first of all, identify, hey, when are we looking at a quadratic function? One thing you might look at sometime is an equation. And if we have like a function f of x equals x squared, and that's the highest degree, so we have a degree 2 polynomial, then that's a quadratic. Okay, if it has an x squared. If we add an x cubed or an x to the 4, then it's not a quadratic anymore. It would be a quartic or a cubic. So anyway, now we're going to have three main forms of these quadratics, and so one might look like f of x, a function of x, is equal to a multiplied by x squared plus b multiplied by x plus c. You want to write this form down now, okay? And this is the result of simplifying any other quadratic fully. You're going to get a standard form quadratic. We might also encounter factored form quadratics, and they look like this. We're going to call this one g of x is equal to a. It's the same a in all cases. If you change the quadratics form, the a is going to be the same in each form. This is a cool property. X minus r and x minus s. Okay, and the cool thing about these are that r 0 and s 0, these 2 points are the roots, or the zeros, or the x-intercepts of your quadratic. Okay? And that's a cool fact. You can see them in factored form. That's the beautiful thing about factored form. Oh, another thing about standard form. Just going back to standard form here for a second. The point 0c gives you the y-intercept, the place where it crosses the y-axis. Okay, so that comes from standard form. And then there's vertex form. And so h of x is equal to a, again, x minus h squared plus k. Okay, and the cool thing about this is the point h, k is the vertex. Okay, this point, the highest point that my ball gets after I kick it. All right, let's keep going. Well, something to note, these ones, when we have a minus in the form, like those minuses there, we have to flip their sign to get them into these points. Notice this is positive r, this is positive s, and we have minus r there. There's been a sign flippage. There hasn't been a sign flippage with k. There hasn't been a sign flippage with c. Those tell the truth, and the ones with minuses lie. That's how I've heard some teachers explain it. I don't know how a number is ever supposed to lie to you, though. I think people just get confused. Okay, let's keep going. Graphs, on the other hand, sometimes we're going to look at a graph, all right? And a graph might look something like this, folks. Okay, where we have a wee like that, okay? And we might want to identify things like the roots, so I'll do the roots in orange. So these are the roots here. Or they're called the zeros, or the x-intercepts, or the solutions to the quadratic, but I don't want to write down a fourth name for this thing. Calling them the roots is fine. Okay, and those you can see those in factored form. There's also a vertex. We'll say the vertex of this one is down there. I kind of wish I didn't put it right next to the y-axis. And these also have y-intercepts, which we get, here 0c. This is the initial value, or y-intercept. Two names for that point is plenty. We call it the initial value because that might be like when I kick the ball, it's at that height, or when I launch the rocket or something like that. It's times 0 because x, this x-axis will often be time, and the f of x-axis or y-axis is going to be height or something. Okay, and then these also have like an axis of symmetry, and this one's axis of symmetry is really close to the y-axis. We call that the axis of symmetry. So these are kind of the anatomy of the parabola. We'd have those there. I'll draw a better one. Here like this. Here's the vertex. Here's the axis of symmetry. Here's the y-intercept, okay? All right. OS, the axis of symmetry. And the last place we might remember our course is equations, graphs, and tables. These are our bread, butter, and slicey cheese. Okay, we can do a lot with these three ingredients. So a table of values, we also want to be able to look at a table of values and identify is it a quadratic or not. And you're going to investigate the second differences. They should be constant and non-zero. What does that mean, Mr. Jennings? Excellent question, middle-aged student. All right, so let's look at some tables and I'll show you what I mean by second differences. First differences are where I analyze this and I say, -8 went to -3. That day got 3 warmer. -5 to -2, 3 warmer. -2 to 1, 3 warmer. Water just started melting. 1 to 4, 3 warmer. 4 to 7, not beach weather yet, but we're getting there. 7 to 10, 3. So +3 all the way down. Those are called first differences. The differences between the y, or the f of x values, gives you your first differences. But then we can take that a step further and we can analyze second differences. 3 went to 3, that changed not at all. 3 went to 3, that changed not at all. Changed not at all. Changed not at all. Changed not at all. The rate at which it changed did not change. Okay, so it was rising by 3 degrees at a constant rate. The rate itself never changed. So these are second differences. And they're constant, but they're 0. So this function is linear. A linear function has constant first differences, which are non-zero, unless it's a horizontal line. Okay, how about we investigate the next one, everybody? So this one here, I'm a 17-degree day that's now 7 degrees. I'm 10 degrees colder. Woof! And then it gets colder still. 7 goes down to 1, that's -6. 1 goes down to -1, that's -2. Oh, don't worry, the temperature's coming back up again, it seems. It's now 2 degrees. The temperature goes from 1 to 7, that's an increase of 6. And then from 7 to 17, that's an increase of 10. Cool. What we've got here are some second differences, which get bigger by 4, 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 and 6 and 10 get bigger by 4. Okay? So this one has constant second differences that are non-zero. So this one is absolutely quadratic. And we can see that it's constantly changing, but the rate at which the f of x values are changing the rate is changing. And the rate is changing by 4 at every step. That's why you get a curve. That's why you get a curve with a really predictable pattern, because the rate at which the curve changes is constant. Yeah, that's right. Okay, now let's check this one out. Okay, so this one, same color scheme here. This one got smaller by 4. This one got bigger by 4. Oh wait, this one got smaller by 1. This one got bigger by 5. This one got bigger by 1. This one got bigger by 5. Ooh, wow. Let's investigate our second differences and see what we get. Minus 4 to 4, that got bigger by 8. 4 to minus 1, that got smaller by 5. Minus 1 to 5, that got bigger by 6. 5 to 1, that got smaller by 4. 1 to 5, that got bigger by 4. This is all over the place. This is like, I don't know, pretty weird. It's nonlinear, non-quadratic. And after doing that little bit of analysis, I couldn't tell you what the next value was supposed to be. I can't see anything in that. Okay, so let's talk about domain and range of some of these functions. Okay, so the domain and the range, all right, we can see here, let's talk about the quadratic one. That one there. So I'm going to look at this. See, that's our lowest value. All right, and that's going to be related to the range. The domain starts at minus 3 and goes to 3. So we will probably say x is of the integers, and we have minus 3, minus 2, minus 1, 0, 1, 2, and 3 gives us our domain and the range. Y is also of the integers, and it could be minus 1, 1, 7, or 17. That's how we would state the domain and range for those. That's that. Okay, let's keep going. All right, now we want to have the skill of being able to fill in a table of values and then graph the relation. You graph the function. Okay, let's start with this one. F of x is x squared. I'm going to ask your faithful supply teacher to pause the video, and then you can fill in your tables of values for f of x is x squared and g of x is negative 2x squared plus 12x minus 10. And then when you resume the video, I will have mine done as well. So I'm going to pause my video, do these, and you're going to do them. Okay, I got the first one done. So let's take a look. So it's pretty straightforward in that if we square minus 3, we get positive 9. So that's the point minus 3, 9. Right? Just put the x in first and the y in second. And then here's minus 2 squaring to 4. There's a minus 1 squaring to 1. 0 squares to 0. 1 squares to 1. 2 squares to 4. And 3 squares to 9. All right. If we do some analysis on this, so we're going to go back to our beauty color scheme here. That got smaller by 5, smaller by 3, smaller by 1, bigger by 1, bigger by 3, bigger by 5. When people talk about the step pattern of these, they're usually talking about these numbers. Like, as we leave the vertex, what happens to the parabola? Okay, and here we have 1, 3, 5. If we went ahead and analyzed the second differences, we'd see that got bigger by 2, 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 and that got bigger by 2. So we are quadratic, of course, because we can look at that and see it's quadratic. And we can look at this shape and see it's quadratic. And then we can go ahead and identify the vertex here. The vertex is the turning point, the point where it's kind of flat, and that's 0, 0. So we would write that in as a point. The maximum or minimum, it has a minimum and its minimum is f at 0 equals 0, just this point 0, 0 is its minimum value. Its zeros are the same. It's 0, it crosses the y-axis there and only has 1. Its y-intercept is the same. It's also 0, 0. Its axis of symmetry is the line x equals 0. Okay, this line is the line that divides the parabola in half, and those are all the points where x is equal to 0. It's really just, you say x equals, x equals that value, the value of the h, or the value of the x value of the vertex. Okay, and then the step pattern, 1, 3, 5. And the step pattern is referring to this sort of phenomenon where I go over 1, up 1, over 1, up 3, over 1, up 5, and we see a kind of stepping up in that sense. Okay, so that's how you do that one. All right, now let's do the next one in green, since I happen to have my green pen up. And what I would do is just copy out g of x is equal to negative 2x squared plus 12x minus 10. And then I'm just going to go ahead and, so I can visualize it, take these numbers. Okay, 0 is really easy. 0, 0. 0 squared is 0, times something by 0, it's 0, so that's minus 10. Okay, minus 10. And then after I've done 0, I can do 1, right? 1 times minus 2 plus 12 times 1 minus 10 happens to equal, well, that's g at 1. And that happens to equal minus 1 plus 10. This is also 0. That's very interesting. That's 0. So that is 0 there. So there's one of the zeros. Cool. All right, now let's try g at 2. Okay, so I just go ahead and I'll erase these. Right? And then we're going to go ahead and put 2 in there. So we put 2 in for here, 2 in for there. And maybe we need to, oh, this is squared as well. To square it. Did I square it last time? Oh, it's 1, doesn't matter. Okay, so here, negative 2 times 2 times 2, so negative 2 times 2 squared is negative 8. 12 times 2 is plus 24, and minus 10. So that's 6. So this one is 6. So got bigger by 10, got bigger by 6. I bet the next one gets bigger by 2. Okay, 3. So probably going to be 8 here, isn't it? So let's go ahead, we'll put those things in. See how efficient it is. It's just so efficient. 3, let's have this g at 3, okay? 3 squared is 9, 9 times minus 2 is minus 18, 12 times 3 is plus 36, and when we do that, it's 36 minus 28 is indeed 8. Oh, just as predicted, 8. Okay. Now I bet it goes down by 2. I'm using the step pattern here. Okay, what am I talking about? Bigger by 10. Okay, plus 10. Bigger by 6. Bigger by 2. Ooh, what did I said 2 and I wrote 6. 2. Okay. Now, here's the pattern that I'm noticing. All right. Get smaller by 4. Smaller by 4. What's smaller by 4 here? Be minus 2. Okay, so minus 2 here, and then smaller by another 4, so minus 6, and smaller by another 4, minus 10. Now I can use that to fill in the rest of the table of values and be real sneaky, right? Because this math, you notice patterns and then use the patterns and make this work easy. Okay, so this one here, I expect it's going to be 6, and then we're going to take away 6 from that. Oh, there's another 0, and then we take away 10 from that. Oh, there's minus 10. Okay, let's check and make sure. We're going to check with this one, just to make sure we've applied our pattern correctly, and that we've got that all right. So I'm just going to remove all that. And we're going to put in 6 here. G at 6 is going to be negative 2 times 6 squared. That's negative 72. Your calculator will tell you the same thing. 12 times 6, oh, that's also 72, but that's positive. 72 minus 72 is minus 10. Oh, look, we thought it would be minus 10 because we did this pattern. and we see the connections, and then we're having fun because we're seeing connections, we're getting things right, and we're liking that feeling. So good, do things the way I do because I enjoy them. If you don't enjoy them, do them my way, and you might start enjoying them. All right, now we plot these points. 0, minus 10, so that's way down there. Oh my goodness, that's so low. 1, 0, wow, just jumps right up there. Okay, 2, 6, oh, it's even above that other parabola for a shining moment. 3, 8, oh, we were almost at that other parabola, we crossed back. Okay, and then we're down here, and then we're down here again, and then we're symmetrical over there. I could also use symmetry to plot that. And then this looks like, I struggle so much drawing these beautifully on my tablet. Yep, at the point. Oh, this is not bad. Not bad, if I do say so myself. It goes off to infinity in that way, like that. Okay, so there's our graph. From this graph, we can see there is vertex. That's the point 3, 8. So that's our vertex. Let's put that in there, 3, 8. Our maximum and minimum, it's a maximum value. And that's f at 3 produces a maximum, that's 8. Okay, that's this point. That's the maximum this ever gets to. It's the highest the ball goes. The maximum profit or whatever. The zeros here are 1, 0 and 5, 0. The y-intercept is 0 in the x, of course, minus 10 in the y. The axis of symmetry is this line here. X is equal to 3. And the step pattern is, this is what we're talking about, the step pattern, minus 2, minus 6, minus 10. The steps away from the vertex. Okay, visualizing that, it would look something there. Okay, something like this: over 1, down 2, over 1, down 6, over 1, down 10. Okay, that's down 2, down 6, down 10. And that's what people mean when they talk about step pattern. It's the first differences as you leave the vertex. I think that's what people mean when they talk about step pattern. So, in summary, practicing quadratics is cool. Try these. You can write your own notes in there that help you remember things. They could include words like vertex, roots, axis of symmetry, forms, graphs, tables, equations, etc. Okay, go give these a try. And let me know if you have any questions. Bye for now, everybody. No, not there. Over here. Bye.